This is the vlog for our lab E4 state machine design. We are group 13 and this is our details. So let's start it. For our part 1, we are supposed to build a MOSFET machine that will provide us with these sequences of signals based on the stepping sequence. So from this stepping sequence we can see that this is our truth table and this is our state diagram. So we can see that S0 should be, S0 should be 1 0 0 0, S1 should be 0 0 1 0, S2 should be 0 1 0 0, S3 should be 0 0 0 1. Why do we get it? We get it from here. For S0 it is 1 0 0 0, for S1 it's 0 0 1 0, for S2 it's 0 1 0 0, for S3 it's 0 0 0 1. Now for our output, this is our output function. So we get 4 outputs which are O0, O1, O2 and O3. So for our O0, if we want to get an output of 1 for O0, our B should be 0 and A should be 0 as well. So our output should be O0 is equal to A bar B bar. For our O2, if we want to get 1, our B should be 1 and A should be 0. So our output for O2 should be AB bar. For our O1, if you want to get 1, our A should be 0, B should be 1. So our output should be A bar B. And for our O3, which is 0 0 0 1, our B should be 1 and A should be 1 as well. So our output should be BA. So based on all the sequences and data we got, we have built the schematic for our circuit. In here we have used one 107 IC, which is a dual JK flip-flop, XOR gate, NAND gates and NAND gates and AND gates. So if our circuit works, we will be getting a clockwise sequence for when our clock is 1, and for 0 we will be getting an anti-clockwise sequence. So let's check it out. Based on the schematics, we have built our circuit for lab part 1. So we can see when our input for the clock module is 0, we are getting a sequence in the anti-clockwise direction. Now see, it's working in the anti-clockwise direction. Now for when our input for the clock module is 1, we are getting a sequence working in the clockwise direction. Let's see it again. So yeah, now our clock module is 1 and it's working in the clockwise direction, and if we change it again to 0, it will go in the anti-clockwise direction. Let's see. So our circuit works. This is the part 2 for our lab E4. So we are supposed to build 2 circuits for this part. The first one should be a 3-bit linear feedback shift resistor. So from here we can see for an n-bit resistor we are supposed to get 2 to the power n minus 1 states. That means for a 3-bit resistor we are supposed to get 7 states. So this is the oscilloscope reading that we are hoping to get, and we can see that these are the seven states that we are supposed to get. The first one is 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. So this is the state diagram, and the 0, 0, 0 is another state. So if we build this circuit where x3 is equal to x1 XOR x0, then we are supposed to be getting a loop of 0, 0, 0. In order to remove that loop, what we need to do is we need to connect this XOR gate to a high logic level. That means we need to connect it to a switch and then input 1 instead of 0. Then we're supposed to get 7 steps. And for the next part, we are supposed to build a 7-bit LFSR with a sequence length of 127. And for that, we are supposed to be using x3 XOR x0, and then input it as x7. Now this is the schematic for our both parts for part 2. So here we have used a 3-bit shift resistor. So here we can see x1 and x0 are connected via a XOR gate, and then that XOR gate is connected to another one, and in order to remove the 0, 0, 0 loop, we connected this XOR gate to a switch from where we can enable the input to 1, and then the output of this XOR gate is connected to the D1, and D2 is connected to VCC. And for our part 2, we have created this circuit using a 7-bit shift resistor. We have moved 2 ways because for this circuit we need to actually connect x3 and x0 in XOR with a XOR gate. So here we have connected the x0 and x3 with a XOR gate, and the output also has been connected to another XOR gate, which is connected to a switch in order to make it make the input high. Then the output is connected to D1 and VCC is connected to D2. So let's check if our circuit works or not. So this is the part 2 for our lab E4. Here the teacher has already built the circuit for us, and now we are going to see it. Now from the circuit we can see that this circuit actually works, and the teacher has already connected it to the oscilloscope. Now we can clearly see the signals. The yellow signal is our clock signal and the purple one is our output signal. Now if the teacher master resets the whole shift resistor, then we won't be able to see any signal for our output. That is because when we reset the circuit, the whole thing goes into a loop of 0, 0, 0, and because of that we don't actually get any signal for it. And in order to remove this loop, what we need to do is we are going to jumpstart the whole circuit, and for that we are going to use the extra XOR gate. So for our 3-bit shift resistor, what we are going to do is, after connecting the X1 and X0 using a XOR gate. We are going to connect that output to another XOR gate, and that XOR gate is going to be connected to a switch, and through the switch what we are going to do is we are going to input active high logic. That means we are going to input 1, and the circuit has already jump started and we can see the signals again. Now if we look at the oscilloscope screen, we can clearly see that from this circuit we are getting a clear pattern in the signals. That means the signals aren't random. Although if we were physically in the lab, we won't be able to see this because of the noise of the oscilloscope, but as we are watching it using a video, it is clear to us that this signal is not random and it has a clear pattern to it. Now so that means this part for part 2 is working. Now let's move to the next part, where we will be building a 7-bit shift register with 127 sequences. For that, the teacher has already built the circuit here and connected it with the oscilloscope. Now the teacher will again reset the whole circuit and then jumpstart the circuit in order to get the signal into the oscilloscope. So here we can see that after jump starting the circuit we are getting a signal, but clearly this time there is no pattern in the signal. So that means our 7-bit shift register does not give us a sequence or a signal sequence that has a clear pattern. That means it is giving us a random signal. But as we are watching it through the video, what we cannot see is actually there are 2 points in the oscilloscope screen where the value is always fixed. Although the teacher can see it, we cannot see that here. The teacher will now show it that there are 2 points where the signals are always fixed. And that is why we cannot actually call this signal a random signal. These kind of signals are actually pseudo-random signals. That means for some points they show a fixed pattern, and for some other points they do not actually clearly show a random pattern. So that means these kind of signal are not random and they do not these kind of signals do not show any clear pattern, or we cannot even say that they are random, because for some points they are showing us fixed points, fixed signals, fixed values. So that means for our lab part 2, the first circuit that we built gave us a clearly signal that had a pattern, and for the second part we are getting a pseudo-random pattern. That means the signal is not random, yet the signal has a pattern at some fixed points. In our case we are getting fixed values at 2 points. The teacher has already shown it. So that is the end of our part 2. So this is the lab part 3 for our lab E4. So what we are going to do in this part is we are going to connect the circuit from our part 2 using with D-type flip-flops, and then detect the sequence for 0, 1, 1. and check if the circuit works or not. So this is the schematic for our part 3. Now let's go to the circuit. So this is the part 3 for our lab E4. So here we have built the lab part 2 circuit and added some D flip-flops in order to find out the sequence 0 1 1. So now we have connected to oscilloscopes with our circuit to find out the sequence 0 1 1. Now if we look at the oscilloscope, we can see that if we look at the upper oscilloscope, the yellow signal is our F and the purple one is the data signals. So when we zoom our signal, we can see that now if we zoom the oscilloscope, then what we can see that for 0 1 1 we are getting high here and high reading, but for 0 0 1 we are getting a false reading here. That is because after 0 0 1 it cannot go to 0 again, and that is why it is showing a false signal, and that is why it will affect how we get the signal in our second oscilloscope. So from the second oscilloscope we can see for one cycle signal we are also getting some extra values. So here we can see that for one clock cycle we are supposed to get our output. We are getting our output, but we are also getting extra spikes. That is our false output. That is because for our noisy input and the state conditions are affecting with our outputs. That is why we are getting so many false outputs. That is affecting the output that we are get. So we have detected 0 1 1 using the flip-flop and the circuit from our part 2. So that is the part 3 for us, but the problem is we are getting a lot of extra spikes that are known as the false outputs.